In this video, we'll be looking at the question of how to find tangents to polar curves. So the question is, given a polar curve, r equals f of theta, how do we find dy dx? Well, the key is to use what we know about finding dy dx in terms of parametric equations, and to first convert our polar curve to a set of parametric equations. Okay, so we said we wanted to write our curve here in parametric form. So recall that when we looked at converting between polar coordinates and rectangular coordinates, we had the conversion that x was equal to r cosine theta and y was equal to r sine theta. So we can use for our parametric equations that x here is equal to r cosine theta, where r is our f of theta. So our x will be f of theta cosine theta, and our y will be f of theta sine theta. So using this, we can say that dy dx will be equal to dy d theta divided by dx d theta, our change in the vertical component over the change in the horizontal component. And then we can use the product rule on these parametric equations here. So dy d theta, our derivative of f of theta sine theta, would be f of theta, the first here, times the derivative of sine theta, cosine theta, plus sine theta times f prime of theta. And then this would be divided by our derivative of x here, dx d theta. So I'd have f of theta times negative sine theta plus f prime of theta times cosine theta. Okay, so we don't actually have to remember that this whole rule over here, as long as we remember how to find our parametric equations here. Given my polar curve, I can write down x is equal to f of theta cosine theta, y is equal to f of theta sine theta, and then find dy dx by doing dy d theta over dx d theta, just like we would for a set of parametric equations. Okay, so we're just going to look at a few more facts here associated with tangents, and then we'll look at one example. So looking at this form of the derivative that we got, we see that it could become a little bit simpler in the case that f of theta is equal to 0. So what if f of theta is equal to 0? What does that mean? Well, this means that r is 0. Okay, so if the radius is 0, we're talking about the location of the point being at the origin. Okay, so in this case, you would have dy dx just equal to f prime of theta sine theta all over f prime of theta cosine theta. Okay, and this is just going to equal tan theta. Okay, we can cancel the f prime theta over the f prime of theta here, as long as our f prime of theta is not 0, right? So as long as we're not going to have some issue with dividing by 0, that can just simplify to tangent of theta. Okay, so what is the meaning of this? Well, in the case that f of theta equals 0, our dy dx here represents the slope of the tangent line to the curve at the pole. Remember, the pole is what we call the origin in terms of our polar coordinates. Okay, and theta equals our angle here, some angle here, where f of theta equals 0 is the tangent line. That's like the equation of the tangent line in polar coordinates at the pole. Okay, so I'm just going to draw a picture to give you one example. Let's say my curve looks like this here. Maybe I have a loop that goes into my my pole here. So I would actually have, in this case, these two tangent lines at the pole. Okay, two places where r would be equal to 0, and I'd have theta equals some angle here, let's call it alpha, and theta equals some angle here, let's call it beta, and then tangent of that angle in each case would be the slope of that tangent line. Okay, so when we look at some problems later, we'll be interested in when the curve hits the pole. Okay, we'll be interested in essentially the angle in which our curve goes into the pole. That'll be helpful in doing some curve sketching type problems. Okay, so we have that special case where tangent theta there is representing the slope of our tangent lines at the pole. Okay, so what's one other key fact we want to talk about? Well, when we've talked about tangents for our parametric curves, we also talked about special tangents like the horizontal and vertical tangents. So because we can convert our polar curve to being in the parametric form, the locations of our horizontal and vertical tangents are determined in the same way they were for those parametric curves. So we have horizontal tangents where dy d theta is 0, provided dx d theta is not 0, and vertical tangents where dx d theta is 0, provided dy d theta is not 0. And we know if both of those are 0, dy d theta and dx d theta equals 0, then we have to look at the limit of dy dx. Okay, so that's just a reminder on what we would do in that situation. So let's just look at one example where we're actually going to find the tangent line for a particular polar curve. Okay, so here we have, for the polar curve, 1 plus cosine theta. We're interested in finding the slope of the tangent line at theta equals pi sixth. Okay, so we're going to have to find dy dx and also evaluate it at this particular theta value. So if I'm going to need to find the slope, okay, I said that means I need to find dy dx, which means I need to have an x and a y here. So my x I know is equal to r cosine theta, but here my r is actually equal to, and here I'm going to write it under instead of next to. This means I have x is equal to 1 plus cosine theta, okay, for my x parametric curve. I also know I have the conversion y is equal to r sine theta, so that means my y will be equal to 1 plus cosine theta, because that's the value of my r for the polar curve, times sine theta. Okay, so to find dy dx, we know we're going to be doing dy d theta over dx d theta. So our dy d theta will involve our product rule. So I'm going to have that first function times the derivative of the second function, so times cosine theta, plus my sine theta here times the derivative of 1 plus cosine theta. So I'll have negative sine theta times sine theta. Okay, and this will be divided by our dx d theta. So again, I'll have 1 plus cosine theta So we'll have 1 plus cosine theta times the derivative of cosine theta, so that's negative sine theta, plus we'll have cosine theta here times the derivative of 1 plus cosine theta, so that'll be negative sine theta here times cosine theta. Okay, so we can try to simplify this a little bit before I start plugging in my particular theta value. I'll have cosine theta plus cosine squared theta minus sine squared theta. Let's see, what will this be divided by? Well, I have a negative sine theta within both of these terms, so I could factor out a negative sine theta, and then that would be times a 1 plus cosine theta plus cosine theta, so I'd have a 1 plus 2 cosine theta that I'd be multiplying by. That's about as simple as we can get this, but that might help just a little bit for doing the arithmetic. So I'm going to do dy dx evaluated at my theta value of theta equals pi sixth. So I'm going to have cosine of pi sixth, which is root 3 over 2. Again, cosine of pi sixth is root 3 over 2, so this will be root 3 over 2 squared, so that'll be 3/4. Sine of pi sixth is 1/2, so I'll have 1/2 squared, or 1/4. Again, sine of pi sixth is 1/2, so this will be -1/2 times 1 plus 2 times cosine of pi sixth. Cosine of pi sixth is root 3 over 2. 2 times root 3 over 2 means I'm going to have our root 3 there. So we can just look at simplifying this a little bit. Notice that my numerator here is going to be root 3 over 2 plus 1/2. Okay, or I could write that as root 3 plus 1 over 2. Okay, notice that 3/4 minus 1/4 is going to be 2/4, or 1/2, so we have root 3 over 2 plus 1/2. This is going to be divided by this negative 1/2 times 1 plus root 3, or I could look at that as times the reciprocal, so times -2 over 1 plus root 3. So we notice how that 1 plus root 3 and 1 plus root 3 cancel. So I'm left with -2 over 2, which simplifies to my slope here of -1. Okay, so we found that our slope equals -1 at theta equals pi 6. Okay. If you wanted to see what this looks like on the graph, remember this curve here, if you took a look at that list of the special polar curves, and we have something like a plus b cosine theta, where a divided by b is equal to 1, we're going to have one of those cardioids. Okay, we could also see that if we plotted a few points and used symmetry like we did in one of our earlier examples. This is a cardioid, and it's traced out on the interval from 0 to 2 pi. So we could get a quick sketch here. R equals 1 plus cosine theta. So notice that when cosine is 0, r would be equal to 2. Here at theta equals 0. When theta equals pi over 2, notice that cosine of pi over 2 is 0. So I would have an r of 1 there at pi over 2. At pi, cosine of pi would be -1, so I'd have an r of 0 there. Okay, and then at 3 pi over 2, cosine of 3 pi over 2 is 0, so I'd have this angle of 3 pi over 2 and a distance out of 1, so that would put us, right down here. So this is theta equals 3 pi over 2. We said we know that this is going to have the shape of this cardioid. So it's doing something like this here. So theta equals pi 6, somewhere around, somewhere around here. Okay, so we can just sort of get a little sketch here of what our tangent line looks like, something like this. So I can just see that I do have that negative slope thereof, which turns out to be a slope of -1 at that particular theta value. Okay, so let me know if you have any questions on this material.